A green, elongated, and silent object travels through the solar system at a speed that breaks all known limits. It does not belong to our sun, it was not born in our cosmic neighborhood, and yet it traverses its heart as if following a destiny traced billions of years ago. This visitor is called 3I Atlas, and its presence is rewriting what we thought we knew about interstellar comets. Discovered by the Atlas tracking system, this body travels at nearly 58 kilometers per second, a speed so high that no object gravitationally bound to the sun could sustain it. Its hyperbolic trajectory confirms an undeniable fact. 3I Atlas comes from another place in the galaxy, a wandering fragment from an unknown system that, through an astronomical coincidence, now crosses ours. But why has it captured so much attention from astronomers? Because its behavior does not fit any previous model. Its brightness increased long before it approached the sun. Its tail seems to defy the direction of the solar wind, and its chemical composition suggests a mixture of materials that does not match anything seen before in the solar system. Every piece of data collected reveals a story of deep origins, possibly in ancient regions of the Milky Way. What is happening with 3I Atlas is not just another observation. It is a reminder that the cosmos still holds secrets that not even the most advanced science has managed to decipher. And today the question resonates all over the world: what is really happening with 3I Atlas? Before we dive into this video, you need to do 3 things immediately to activate the scientific community. First, give a like to this video to promote this discovery to more observers. Second, subscribe and activate the notification bell to receive the next updates on the real-time tracking. And third, go down to the comments right now and write Cosmos to join the global registry of those who are following this historic event. Do it now. 3I Atlas is not just any comet. It is an interstellar traveler, an object not born under the influence of the sun, but in some remote location of our galaxy. What makes it so fascinating is not only its provenance, but the way it is changing our understanding of the cosmos. Since its discovery, telescopes from NASA, ESA, and independent observatories have followed every movement of this visitor with a precision never before applied to an outsider comet. Unlike common comets, 3I Atlas does not follow a cycle that brings it back. Its hyperbolic trajectory will lead it to abandon the solar system forever, leaving behind only traces of data, images, and questions. Each passing day offers us a unique opportunity to study how an object formed under conditions completely distinct from the solar environment behaves. In this documentary, we will analyze its current journey, its composition, its origin, and the reasons why scientists consider it one of the most significant findings of recent years. Behind its greenish glow and extreme speed, 3I Atlas could be revealing secrets about the most ancient past of the galaxy. Prepare to explore the details that explain what is really happening with 3I Atlas. On the immense stage of the cosmos, where planets spin obeying ancient laws and stars are born and die in a perpetual cycle, an unexpected visitor has crossed the frontier of our solar system. Its name is 3I Atlas, a brilliant interstellar comet that has awakened the attention of the entire international scientific community. Unlike the millions of comets that orbit our sun in elliptical trajectories, this object does not belong to our cosmic neighborhood. Its origin is external, possibly in a remote stellar system, and its fleeting passage represents an unrepeatable opportunity to study material formed in another corner of the galaxy. The designation 3I indicates it is the third interstellar object officially identified by science. Before it came 2 visitors, the mysterious one discovered in 2017 and the comet 2I Borisov, found in 2019. However, 3I Atlas stands out among them for its size, its luminosity, and the complexity of its behavior. It was detected by the Atlas tracking system, a set of automated telescopes designed to find objects potentially dangerous for Earth. But what the astronomers found was not a threat, but a window to the galactic past. Since its identification, multiple observatories on the ground and in space have focused their attention on this elongated body of emerald green color traveling at a speed of nearly 58 kilometers per second. This speed is too high for the sun to retain it, which confirms its interstellar nature. In other words, 3I Atlas is not gravitationally bound to our star, it is just passing through. It arrived from deep regions of the Milky Way, and after crossing the heart of our system, it will continue its journey into interstellar space, never to return. What makes it so special is not only its provenance, but the physical and chemical signals it has shown since its arrival. Astronomers noted that it began to activate, that is, to release gases and dust, much earlier than happens with a typical comet. Normally, A comet starts to sublimate its ice and form a coma when it approaches the orbit of Jupiter or further in, where solar heat intensifies. But 3I Atlas was already showing activity far beyond that distance. This means its ices are different, formed by substances that evaporate at lower temperatures, like carbon dioxide or carbon monoxide instead of water. That difference is a direct clue about the environment in which it was born. The first spectra obtained showed an anomalous composition. Its light revealed an unusual type of polarization, suggesting that the particles reflecting sunlight are more porous or have a structure different from that of solar system comets. This seemingly technical detail is of enormous value for astronomy, because it means we are seeing dust and materials that formed under conditions different from those existing near the Sun. In a certain sense, observing 3I Atlas is like looking at an interstellar time capsule. The images captured by the TESS telescope and later by terrestrial instruments showed a bright halo surrounding the comet's nucleus, which confirmed intense activity even at great distances. As it approached the Sun, its brightness increased in an unpredictable manner, something scientists are still trying to model with precision. It was not a simple light variation. It was an explosion of energy that evidenced a chemical change inside the comet, possibly due to the sudden increase of water vapor as temperatures rose. This behavior, combined with its greenish color, led several researchers to consider it the most dynamic and complex of all interstellar objects detected so far. Unlike Oumuamua, whose surface seemed dry and without a visible coma, or Borisov, which showed more conventional behavior, 3I Atlas combines characteristics of both, the speed and rarity of the first and the intense activity of the second. It is a cosmic hybrid, a witness to processes that Earth could never reproduce. Throughout the months preceding its perihelion, its point of maximum approach to the Sun, which occurs at 1.4 astronomical units within the orbit of Mars, scientists have followed every variation in its brightness and direction. 3I Atlas travels along a trajectory almost lateral with respect to the plane of the ecliptic, an uncommon entry, almost as if it had struck the solar system from the side. Its passage is so swift that it remains only weeks in the visible zone before heading back into the galactic darkness. This event, though brief in human time, represents a scientific milestone. For the first time, it is possible to observe how an interstellar comet reacts to solar radiation, how its composition changes, and how its materials transform upon facing the heat of a star. Every photon it emits, every particle it releases, carries information about its internal structure and about the environment in which it formed, perhaps more than 7 billion years ago in an ancient region of the Milky Way's thick disk. Scientific institutions have coordinated an international observation network. The James Webb Telescope, Hubble, the VLT in Chile, and several radio telescopes in Europe and North America have collaborated to obtain simultaneous data. The objective is not only to study a comet, but to analyze the behavior of primordial matter traveling between stars. What is discovered could offer clues about how planetary systems form and how common the materials necessary for life are. While the public looks at the images with awe, scientists process terabytes of information: light spectra, brightness curves, gas emissions, movement patterns. Every piece of data is compared with existing models, and almost all show deviations. 3I Atlas does not fit the known molds. That is precisely its greatest virtue, forcing science to reformulate questions we thought were answered. As the comet approaches its perihelion, the Sun partially hides it, hindering direct observations. During this period, the solar glare acts as a wall of light, preventing optical telescopes from following it. However, infrared and radio instruments can still register faint signals. It is a moment of global expectation. No one knows exactly how the comet will react to the extreme heat. It could fragment, change brightness, or even develop new structures in its coma. 3I Atlas is, in summary, a galactic messenger that has crossed the void to remind us how small our corner of the universe is. Its study not only expands our knowledge about comets, but also about the diversity of the worlds that exist beyond the reach of our probes. Its journey is a story of movement, energy and time. A story that is just beginning to be told. The 29th of October marks one of the most awaited moments of the year for the astronomical community, the perihelion of 3I Atlas, its point of maximum approach to the Sun. It is here that the interstellar visitor reaches the climax of its traverse through the solar system. At this point, it is located at just 1.4 astronomical units from our star, that is, within the orbit of Mars. It may seem an enormous distance to us, but on a cosmic scale it is a dangerous brush. An instant where solar radiation, the stellar wind, and extreme temperature test the resistance of its structure. During this stage, astronomers observe a fascinating phenomenon. Sublimation, the process by which the comet's ices, formed by volatile compounds like carbon dioxide and carbon monoxide, transform directly into gas upon receiving the sun's energy. This phase change releases enormous amounts of particles, forming a luminous envelope around the nucleus known as the coma. The coma is essentially the comet's temporary atmosphere, a cloud of gas and dust that reflects sunlight and gives it that ghostly appearance so astounding in images captured from Earth. In the case of 3I Atlas, the coma is especially bright and extensive. Since its discovery, the instruments of the Hubble telescope and the Subaru Observatory in Hawaii detected a halo unusually large for an object of its size. This indicates that its nucleus releases material with surprising intensity. Models suggest that solar heat penetrates the outer layers, causing gases trapped for billions of years to escape violently into space. Every emission, every fragment that detaches, is recording the thermal history of the comet. However, 3I Atlas faces a significant disadvantage during its perihelion. The light of the sun hides it almost completely. From Earth's perspective, the solar brightness is so intense that even the most advanced telescopes have difficulties observing it directly. During these critical weeks, scientists depend on indirect observations using coronagraphs, instruments designed to block the solar glare and reveal nearby objects, or space telescopes operating in infrared wavelengths. These tools allow the comet's evolution to be followed even when its physical presence is lost behind the curtain of sunlight. The data collected during this period are essential. The sudden increase in the comet's activity suggests it is releasing not only gases, but also metallic particles and complex organic compounds. Every spectral sample becomes a piece of the puzzle about its internal composition. Scientists have identified emission lines corresponding to carbon dioxide, carbon monoxide, and, to a lesser extent, water vapor. This confirms that the ices of 3I Atlas are not dominated by water like solar system comets, but by more volatile compounds that sublimate at much lower temperatures. During perihelion, the dynamics of its tail, the most iconic feature of a comet, also experience drastic changes. Under normal conditions, the solar wind pushes the expelled gas and dust, forming a tail that always points in the direction opposite to the sun. But in the case of 3I Atlas, the first observations showed something unexpected, a tail that at certain moments seemed to head towards the sun. This anomalous behavior perplexed astronomers. One possible explanation is that at the initial distance where it was located, the solar wind was too weak to dominate the gas flow, allowing particles to escape in opposite directions before solar radiation definitively pushed them back. That temporary anti-tail became one of the most discussed images by the scientific community. Numerical simulations published in specialized journals showed that this effect could also be due to the comet's geometry. Its rotation axis and its elongated shape can cause gas jets to exit at unusual angles, generating patterns that defy visual expectations. With the passing of the weeks, 3I Atlas finally developed a more conventional tail, long, narrow, and of a greenish hue, composed mainly of dust particles and ionized molecules. The green color that adorns its halo and its tail is another of its most striking traits. This hue comes from the dissociation of diatomic carbon molecules C2 under the sun's ultraviolet radiation. When these molecules are excited by sunlight, they emit an intense green glow that has been characteristic of many active comets, although in 3I Atlas the intensity of that glow surpasses the average. This phenomenon is not only aesthetic. It offers valuable information about the photochemical processes occurring on the comet's surface and about the relative abundance of carbon in its composition. During the weeks following perihelion, the scientific community expects to detect variations in its activity. Comets usually experience episodes of fragmentation when facing extreme solar heat, especially if their internal structure presents fractures or cavities filled with gas. In the case of 3I Atlas, researchers have noticed oscillations in its brightness that could indicate an irregular rotation or the expulsion of large volumes of material. If confirmed, this could help estimate its density and internal cohesion, key data for understanding how interstellar objects form. But beyond the technical analyses, there is something profoundly symbolic in this moment of 3I Atlas's journey. While its icy body approaches the sun, millions of people on Earth observe images of an object that traveled for eons through interstellar space until briefly finding the light of an alien star. On its path, the comet is undergoing an irreversible transformation. The heat is altering its surface, releasing materials that had not seen light since its formation. It is as if the sun were deciphering its history layer by layer while pushing it back into the galactic void. In this phase, space missions play a crucial role. Although no probe has been sent specifically towards 3I Atlas, solar monitoring instruments, like those of the SOHO Observatory and NASA's stereo probes, have been attentive to its passage. These observatories, designed to study the sun's activity, are capable of capturing objects that approach its immediate environment. If conditions permit, they could record images that, although small, offer valuable information about the behavior of its coma and its tail under intense solar radiation. As the comet completes its passage through perihelion and begins to slowly move away, its brightness may diminish, but the observations will not stop. Astronomers hope that when it emerges again from the solar glare in early December, it will be possible to measure how its composition changed after this extreme exposure. That contrast, the before and after of perihelion, will be one of the most important aspects for evaluating how stellar radiation affects interstellar objects. At this point in its journey, 3I Atlas is no longer just a distant visitor. It has become a natural laboratory that tests our theories about matter, heat, and cosmic evolution. Every second it spends near the sun is a unique opportunity to observe how matter born in another stellar system interacts with the energy of our own star. This encounter, though brief, will be recorded in thousands of observations that scientists will analyze for decades. And as the comet continues its traverse, silent, wrapped in its green glow, humanity observes it from a distance, aware that we will probably not see another like it for a long time. Its passage marks another page in the history of the solar system, a reminder that the universe is full of unknown travelers and that each one of them has a story to tell, written in ice, dust, and light. The discovery of 3I Atlas was not a casual event, but the direct result of the constant sky surveillance that humanity has maintained for decades. The story began with a series of automatic detections made by the Atlas system, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes strategically distributed in Hawaii and Chile. This program, funded by NASA, has a clear objective: to detect objects that may represent an impact risk against Earth. However, 3I Atlas was not approaching us with the intention of threat, but as a messenger from the depths of interstellar space. On the 10th of April 2024, the Atlas detection algorithms registered a luminous point that did not match any known orbit. Its apparent motion was so swift that within hours astronomers understood it could not belong to the solar system. The first measurements of its radial velocity indicated a displacement of more than 58 kilometers per second relative to the Sun, a figure that surpassed the limit necessary to escape its gravitational influence. That speed, combined with an open hyperbolic trajectory, could only mean one thing: the object came from interstellar space. That confirmation generated a wave of excitement in the scientific community. Since the discovery of Oumuamua, astronomers had been waiting for a new opportunity to observe an interstellar visitor with greater clarity. Unlike that first object, whose passage was so fast and its size so small that it could barely be studied, 3I Atlas showed much more favorable characteristics. Its brightness was intense, its estimated size much larger, and its trajectory kept it within observation range for several months. For the first time, humanity had before it a foreign body that could be analyzed in detail. The official confirmation process was completed a few days later, when independent observatories worldwide verified the initial measurements. The Minor Planet Center of the International Astronomical Union announced its designation, 3I, the third known interstellar object, an atlas in honor of the system that detected it. Within hours, the news traveled the planet. The most powerful observatories redirected their instruments towards that new light moving against the background of stars. It was as if a strange visitor had just entered our cosmic neighborhood, bringing with it the history of its home world. Orbital analyses showed that 3I Atlas came from a direction near the galactic center, though not exactly from it. Its trajectory indicated it had traveled through space for millions or even billions of years before crossing the plane of the ecliptic, the thin band where most planets orbit. This detail was especially interesting because it suggested the comet was not a fragment recently ejected from some nearby stellar system, but an ancient body, perhaps formed in the first generations of stars in the Milky Way. The dynamic analysis of its orbit, conducted by the Institute of Astrophysics of the Canary Islands and other research centers, indicated that its inclination and speed did not match any known population of trans-Neptunian objects nor any comet from the Oort cloud. In other words, its origin could not be explained within the framework of our solar system. It came from outside and its trajectory would never return. That characteristic made it a unique witness to the processes that occur beyond the domain of the Sun. The idea of an interstellar object traveling through space is not new. Planetary formation models predict that during the birth of a stellar system, many fragments of rock and ice are ejected into interstellar space due to gravitational interactions with giant planets. These fragments wander the galaxy, crossing from one system to another like cosmic dust on a large scale. However, until a few years ago, we had no direct evidence of their existence. It was only with the arrival of instruments capable of scanning large portions of the sky each night that detections like that of 3I Atlas became possible. As data accumulated, the magnitude of its discovery became more evident. Scientists estimated its nucleus measured between 4.5 and 5.6 kilometers in diameter, making it the largest of the 3 known interstellar visitors. Its mass, although small compared to planets, is sufficient to maintain significant cometary activity, releasing gas and dust that form a coma visible from millions of kilometers away. This size gives it an observational advantage. It allows telescopes to capture clearer signals of its composition, rotation, and behavior under the influence of the Sun. The speed of 3I Atlas, approximately 58 kilometers per second, also differentiates it from its predecessors. It is almost double that recorded for Borisov and considerably greater than that of Oumuamua. This rapidity implies that the energy with which it was ejected from its original system was extraordinary, probably due to a close interaction with a giant planet or with a companion star. Some models suggest it could have been ejected from a dense region of the galaxy, perhaps from the so-called thick disk, a zone composed of very ancient stars formed in the first billions of years of the Milky Way. That possible provenance adds a nuance to its history. If it was truly born in the thick disk, then 3I Atlas could be older than the Sun itself. The approximate dating of that region suggests ages of up to 7,600 million years. That means this comet formed when the galaxy was young, when heavy elements were just beginning to distribute after the first generations of supernovae. What it carries inside, the ices, the metals, the organic compounds, is a direct sample of the primitive chemistry of the cosmos. The spectroscopic analysis of its light reinforced that hypothesis. The absence of certain compounds and the presence of others more volatile, like CO2, indicate that the environment where it formed was much colder and with weaker stellar radiation than that of the Sun. That agrees with the idea of a system situated in a quiet region of the galaxy, where planetary formation processes occurred slowly, without the violence of the more active zones of the galactic disk. Each of these clues makes 3I Atlas an invaluable object for modern science. It not only represents an opportunity to study interstellar matter, but also to understand the processes that molded the chemical evolution of the galaxy. If the comets of our solar system are time capsules that preserve the memory of their formation 4,600 million years ago, then an interstellar comet like this is an even more ancient capsule, a relic from times when Earth did not even exist. With every observation, the mystery deepens. The fact that 3I Atlas is now heading towards the Sun, crossing our planetary space, is an astronomical coincidence of extraordinary proportions. If its trajectory had varied just a few degrees, we would never have detected it. But nature, unpredictable as always, aligned it in such a way that human telescopes could capture its passage. And that brief instant, just a few months in its journey of billions of years, is allowing us to contemplate something that transcends the human scale. In its journey, 3I Atlas has not only awakened scientific questions, but also philosophical ones. How many of these travelers cross the void silently unseen? How many cosmic stories are lost in the darkness, waiting for the chance of a detection? Every interstellar object we find reminds us that the universe is dynamic, that stellar systems are not isolated entities, but nodes of a galactic network in which matter constantly flows. In that flow, fragments like 3I Atlas carry with them the vestiges of worlds that perhaps no longer exist. Yes, its discovery is not only a technical achievement but a connection between systems, a tangible sample of the material unity of the cosmos, a fragment of another sun crossing in front of ours, briefly illuminated before disappearing again into the vastness of the galaxy. When 3I Atlas was confirmed as an interstellar object, the immediate comparison with its 2 predecessors was inevitable. Until that moment, humanity had only witnessed 2 visitors from outside the solar system: the mysterious 1I Oumuamua in 2017 and the dynamic 2I Borisov in 2019. However, 3I Atlas distinguishes itself from both in such a marked way that it seems to belong to a completely new category of cosmic travelers. Its size, its behavior, and its interaction with solar radiation defy what we thought we understood about the nature of interstellar bodies. Oumuamua was the first to open this door. Its discovery revolutionized astronomy because it showed a hyperbolic trajectory, clear evidence that it was not bound to the Sun, but its shape and behavior perplexed scientists. It lacked a visible coma, it did not emit detectable gases, and yet it accelerated mildly and inexplicably as it moved away from the Sun. That anomaly gave rise to an avalanche of theories, some scientific and others purely speculative, about its origin and composition. In contrast, Oumuamua and Borisov offered a more familiar spectacle. Its appearance was that of a classic comet, a bright coma, a well-defined tail and predictable activity. However, its speed and its chemical composition, rich in carbon monoxide, confirmed it came from another stellar system. 3I Atlas, however, combines the best and the strangest of both worlds. It is the largest of the three with an estimated diameter of up to 5.6 kilometers, making it comparable in size to the most notable comets of the solar system itself. Its mass allows it to maintain a dense and long-lasting gas atmosphere during its approach to the Sun, producing a glow visible even at great distances. While Oumuamua was an inert rock and Borisov a small but active comet, 3I Atlas is an interstellar colossus that demonstrates extreme activity and surprising stability at the same time. Another fundamental difference is speed. While Borisov crossed the solar system at about 32 kilometers per second and Oumuamua did so at nearly 26, 3I Atlas travels at almost 58 kilometers per second. That speed not only makes it the fastest natural object ever observed traversing our planetary region, but also implies a much greater ejection energy. To achieve such momentum, it must have suffered a violent ejection from its system of origin, probably after a close gravitational encounter with a massive planet or even with a companion star. The direction of its entry is also notable. Unlike its predecessors, which crossed the solar system from trajectories inclined relative to the plane of the ecliptic, 3I Atlas arrived almost laterally, intercepting the plane where the planets orbit at a minimal angle. This orientation places it on a route almost coplanar with Earth's orbit, which facilitates its observation, but also means its trajectory was an extremely precise coincidence. It is as if the comet had grazed our system from the side without impact, but leaving behind a visible trace. That lateral entry produced fascinating observational effects. Telescopes recorded how its tail seemed to shift in a direction almost perpendicular to the solar plane, creating an uncommon geometry. Simulations from the Harvard-Smithsonian Center for Astrophysics showed that this entry angle could have amplified the effects of the solar wind on the coma, generating the appearance of an anti-tail during the first phases of its approach. This behavior, which at the time caused confusion among amateur astronomers, is now understood as a direct consequence of its unique orbital orientation. Another aspect that differentiates 3I Atlas from its predecessors is its composition. While Borisov showed chemical characteristics similar to solar system comets, though with higher abundances of certain volatile compounds, 3I Atlas presents a completely distinct spectral signature. Measurements made by the James Webb Telescope revealed that its coma is dominated by carbon dioxide CO2, which suggests a type of ice formed at extremely low temperatures. This implies that the place where it originated must have been far from its parent star, probably in the icy confines of its original system, where stellar heat barely reached to sublimate water ice. Furthermore, spectroscopic analyses detected an unusually high amount of nickel compared to iron, an imbalance uncommon in known comets. This finding initially perplexed scientists, as both metals are usually found in similar proportions. One of the most accepted theories suggests that the CO2 gases, upon sublimating, preferentially carry nickel atoms, releasing them before iron, which requires higher temperatures to volatilize. Later, when the comet approached the Sun, observations finally registered the presence of iron, balancing the expected relationship between both elements. This process of sequential release offers an unprecedented opportunity to study how different materials behave under extreme conditions of solar radiation. Another notable difference resides in its physical structure. Although no direct high-resolution images of its nucleus have been obtained yet, estimates based on its brightness and light variations suggest that 3I Atlas has an elongated, possibly irregular, but more symmetrical shape than that of Oumuamua. Its rotation seems to be stable with an estimated period of between 10 and 12 hours, indicating it is not fragmenting, at least for now. This stability contrasts with the tendency to crumble that comets approaching too close to the Sun usually show. In the comparative realm, 3I Atlas has also shown a surprising capacity to maintain its structural cohesion. While the comet C 2019 I-4, also designated Atlas though unrelated to this interstellar object, fragmented spectacularly during its solar approach, 3I Atlas has resisted much greater thermal stresses without signs of rupture. This resistance suggests a higher density or a more compact composition, which raises questions about its formation. If it truly comes from a region of the galactic thick disk, it could have formed under higher pressures or from materials different from those we find in local comets. Another key difference lies in the interaction of 3I Atlas with sunlight. Polarization studies indicate it reflects light very differently from most known comets. Its extreme negative polarization suggests that the dust particles in its coma have an unusual texture or size, possibly the product of a different chemical composition or a more ancient thermal history. This trait makes it a natural laboratory for investigating how the optical properties of cosmic dust vary according to their galactic origin. In terms of observation, 3I Atlas has offered astronomers a range of unprecedented opportunities. Its luminosity, greater than expected, allowed even medium-sized telescopes to track it from Earth before the solar brightness hit it. Furthermore, its passage relatively close to Mars, a distance less than that from the red planet to the Sun, opened the possibility that Martian probes captured direct images of its passage. Although initial reports indicate that the cameras of the Perseverance rover and the ExoMars orbiter registered flashes compatible with its presence, the data are still in the process of analysis. Compared to Oumuamua and Borisov, 3I Atlas represents a qualitative leap in the understanding of interstellar visitors. Where the first left unanswered questions and the second offered a partial glimpse, the third combines volume, speed, and composition to offer a more complete portrait of what could be considered a genuine interstellar-type comet. It is not just a solitary traveler, but a tangible sample that matter is exchanged between stellar systems continuously. Its existence confirms that the galaxy is a dynamic space where fragments of ancient worlds cross paths with civilizations that are just beginning to observe the sky. Thus, 3I Atlas not only surpasses its predecessors in size and brightness, but also expands the frontiers of astronomical knowledge. Every difference observed between these three objects reinforces the idea that there is not just one type of interstellar comet, but a wide diversity of materials, structures, and behaviors molded by the unique environments in which they formed. In that diversity perhaps lies the key to understanding the evolution of matter throughout the Milky Way. Understanding where 3I Atlas comes from is trying to follow the trail of a traveler that has crossed countless galactic abysses. Its trajectory, determined by high-precision observations and orbital simulations, points towards a region of the sky near the constellation Hercules, a direction close to the center of the Milky Way. However, this is not a simple astronomical fact. It is the clue that suggests the comet could have originated in one of the most ancient and tranquil places of our galaxy, the so-called thick disk. The thick disk of the Milky Way is a vast structure composed of aged stars, many of them formed more than 8,000 million years ago when the galaxy was still young. Unlike the thin disk, where the Sun and the majority of current stellar systems are found, the thick disk has a lower density and is formed by stars of low metallicity, that is, with a scarce presence of heavy elements. In that environment of calm and stability, collisions were infrequent and primordial materials survived almost intact. If 3I Atlas comes from that region, then it is a witness to the remote past, a galactic relic preserved for eons. Calculations performed by the European Southern Observatory and the Institute of Astrophysics in Paris agree that the entry direction of 3I Atlas aligns with a retrograde orbit relative to the Sun's movement in the galaxy. This means the object does not travel in the same direction as the galactic rotation, but in the opposite sense. This characteristic is typical of bodies that come from older regions with dynamics distinct from those of the current disk. In simple terms, 3I Atlas could be traversing our stellar zone like a fossil moving against the current of the galactic river. Dynamic simulations allow its hypothetical trajectory to be traced back thousands of millions of years in time. According to models from NASA's Center for Near-Earth Object Studies, its current speed and movement vector are consistent with an object that was ejected from its home system after a violent gravitational interaction. At some moment, perhaps 6 or 7,000 million years ago, 3I Atlas orbited a star similar to the Sun or a bit cooler, situated in an outer region of the thick disk. A close encounter with a giant planet comparable to Jupiter or Saturn would have catapulted it into interstellar space, freeing it from its star's attraction and sending it on a journey of no return. During that cosmic exile, the comet traversed interstellar regions where the density of gas is almost null and galactic radiation acts as a constant erosion. In that environment, its outer layers suffered chemical transformations. The most volatile compounds slowly evaporated, while the metallic minerals and more resistant ices remained sealed under a crust hardened by millions of years of exposure to cosmic rays. That is why, when 3I Atlas entered the solar system, its surface showed signs of extreme antiquity, a rough texture and a thermal behavior that differed from young comets formed near the Sun. The most fascinating thing is that despite its age and its intergalactic journey, the comet's nucleus remains surprisingly active. This suggests its inner layers remained isolated and protected from the external environment, conserving materials in their original state. Upon approaching the Sun, those compounds began to sublimate for the first time in thousands of millions of years, releasing gases that had never interacted with any star since their formation. Every emission that spectroscopes detect today represents an exhalation of the galactic past, a direct sample of the primordial chemistry that existed long before the birth of Earth. The hypothesis of its origin in the thick disk is also supported by its chemical composition. Comets formed in ancient regions of the galaxy tend to have a lower proportion of heavy metallic elements and a greater abundance of simple gases like carbon monoxide and carbon dioxide. That agrees with the observations of 3I Atlas, whose coma is dominated precisely by CO2, a compound that sublimes at temperatures much lower than those of water ice. This detail indicates the comet formed in a cold environment, far from any intense heat source, possibly in the outer limits of its system of origin. Thermal models elaborated by the Max Planck Institute for Solar Physics have also proposed that the internal structure of 3I Atlas could contain alternating layers of ice and metallic dust, a configuration that acts as a natural insulator. This arrangement would allow solar heat to penetrate slowly, provoking gradual releases of gas instead of sudden explosions. Such behavior would explain why the comet has shown no signs of fragmentation, despite the extreme temperatures to which it is exposed. From a statistical point of view, the arrival of 3I Atlas to our solar system is an extremely improbable event. Calculations indicate that an interstellar object of this size only traverses the solar neighborhood once every several centuries. This turns its visit into an unrepeatable opportunity for modern astronomers. Every observatory that points its instruments towards this body is aware that a similar event might not be repeated for generations. 3I Atlas has become, in a matter of months, the most studied object in the firmament. Some scientists have suggested that its passage could help us refine models of galactic dynamics. By comparing the comet's speed and direction with known stellar motions, it is possible to obtain information about the gravitational forces acting on a large scale in the Milky Way. In other words, 3I Atlas is not only a messenger from its own system, but also an instrument that reveals how the gravitational fabric of the galaxy behaves. As data is compiled, a consensus begins to take shape. 3I Atlas was probably born in an ancient region of the thick disk. It was ejected thousands of millions of years ago and traveled aimlessly until encountering the Sun by pure gravitational coincidence. That journey turned it into a galactic time capsule, a testimony to the chemical history of the universe before the formation of modern worlds. Its estimated age, between 7 and 7,600 million years, makes it one of the oldest objects ever directly observed. If the calculations are correct, 3I Atlas formed when the Sun did not yet exist and Earth was nothing more than an improbable future in the vastness of space. During that unimaginable time, its nucleus survived intact, conserving the chemical imprints of a time when the first stars were enriching the cosmos with heavy elements. When astronomers observe the greenish glow of 3I Atlas today, they are not only seeing a physical phenomenon, they are contemplating a relic that has traversed the ages. In its interior could be found the same matter that in other places of the galaxy gave origin to planets, moons, and life forms. The comet is not just a visitor, it is a fragment of galactic history that now illuminates our sky. Thus, its origin is not limited to a coordinate in space, but to an epoch in which the universe was younger, colder, and more silent. A time when interstellar dust grains were beginning to unite to form the first worlds. Today, one of those ancient fragments passes before us, reminding us that every star, every planet, and every living being shares the same atoms forged in the fires of stars dead for thousands of millions of years. 3I Atlas, with its journey, its green glow, and its eternal silence, is the tangible proof of that universal connection. A traveler that departed before we existed and that for a brief instant allows us to look towards the most remote past of our galaxy. The first detailed observations of 3I Atlas marked a before and after in the study of interstellar objects. From the moment of its detection, the most advanced instruments in the world were directed towards it with the purpose of analyzing its brightness, its behavior, and above all its composition. Within days, the initial results began to reveal something completely unexpected. This interstellar visitor was not behaving like any known comet. Its activity was unusual, its color unmistakable, and its chemical spectrum simply anomalous. The Test Space Telescope was one of the first to register its presence before it crossed the orbit of Jupiter. In the images, the object already showed a sustained increase in brightness, an unequivocal signal that it was active at distances where normal comets remain inert. This detail perplexed astronomers because cometary activity usually begins only when solar heat is sufficient to sublimate water ice, something that does not occur beyond 5 or 6 astronomical units from the Sun. In contrast, 3I Atlas began to release gas and dust long before reaching that zone. Spectroscopic measurements obtained by the Mauna Kea Observatory in Hawaii showed that its coma, the diffuse cloud surrounding the nucleus, was dominated by carbon dioxide CO2 and carbon monoxide, both compounds that sublimate at extremely low temperatures. That unusual proportion of gases confirmed that 3I Atlas was not made primarily of water ice like solar system comets, but of more volatile ices formed in much colder environments. This finding reinforced the idea that it originated in a distant stellar system where solar radiation was weaker and formation temperatures were considerably lower. The fact that the comet activated so far from the Sun implies that the ices of 3I Atlas had remained sealed under a surface layer that acted as a kind of thermal capsule. During its approach, small fractures in that crust allowed the gas to begin escaping slowly, generating a halo visible even in regions where the Sun barely shone. Every observed emission was like a signal coming from the depths of its structure, a frozen exhalation for thousands of millions of years that now found its release. The greenish color that has so attracted the attention of astronomers and the public is not a simple visual effect. It is related to the presence of diatomic carbon molecules C2, which emit green light when excited by the Sun's ultraviolet radiation. However, in the case of 3I Atlas, the intensity of the green glow is unusually high. This suggests an anomalous abundance of carbon compounds, pointing to a formation environment rich in organic matter. The existence of this type of molecule in an interstellar comet opens fascinating questions about the chemistry of primitive stellar systems and about the possible distribution of the basic compounds of life throughout the galaxy. Another of the most intriguing characteristics observed in 3I Atlas was its extreme negative polarization. In astronomy, the polarization of light reflected by a comet can reveal information about the physical properties of its dust particles: size, shape, texture, and composition. Negative polarization indicates that the particles scatter light in an unusual way, which suggests a more porous or irregular structure than that of typical comets. This result surprised researchers, as no known sample of cometary dust in the solar system presented such a marked pattern. The most plausible explanation is that the dust of 3I Atlas contains materials that do not commonly form in our solar environment. Some models point to it being composed of amorphous silicates mixed with complex organic compounds, possibly analogous to those detected in interstellar molecular clouds. If this is correct, then we are observing for the first time the raw material with which worlds are built in other regions of the galaxy. The observations also revealed something even more unexpected. The comet formed a significant coma long before reaching the inner regions of the solar system, beyond the orbit of Jupiter. This early coma remained stable for months, and its evolution was monitored with precision by optical and infrared telescopes. The surprising thing is that the density of gas and dust increased in a gradual manner, without the brusque peaks that usually accompany the activity of comets as they approach the Sun. This suggests a controlled sublimation process, possibly regulated by alternating inner layers of materials with different melting points. As it approached the Sun, the spectra began to show significant changes. Clear signals of water vapor appeared, an indication that surface temperatures had reached the point necessary to sublimate H2O ice. The interesting thing is that this chemical transition was sudden. The water vapor, absent during the first months, became dominant within weeks. That secondary activation of the comet, observed from different observatories, allowed astronomers to study a poorly understood phenomenon. How do the chemical proportions within an interstellar comet change as it is exposed to levels of solar radiation unknown to it? In the spectra obtained by the James Webb Telescope, weak signals of more complex organic molecules like formaldehyde H2CO and possibly traces of cyanide CN were also detected. Although these detections are still under review, their presence would reinforce the idea that the basic chemical ingredients for life are not exclusive to our system, but common in the material circulating between the stars. Every molecule identified in 3I Atlas becomes a message from the past, direct evidence that organic chemistry is a universal constant. The study of the composition of 3I Atlas was not limited to the visible spectrum. The ALMA radio telescopes in Chile registered emissions in millimeter wavelengths corresponding to carbon monoxide and carbon dioxide. These data helped estimate the gas emission rate, which turned out to be surprisingly high for an object that was just beginning its approach to the Sun. Flow models indicate the comet was releasing hundreds of kilograms of gas per second, an activity comparable to that of the most active known comets, despite being much farther away and coming from a completely distinct environment. The analysis of its total brightness also showed an anomalous evolution. Instead of following the expected curve for a comet in an active phase, a progressive increase as it nears the Sun, 3I Atlas experienced episodes of sudden increase and then stabilization. This variability could be due to the comet's rotation exposing different regions of its surface to solar radiation. If its axis is tilted sharply, some sectors could heat and cool alternately, releasing gas intermittently. In the photometric realm, European observatories registered an oscillating light pattern, a kind of luminous pulse that repeated approximately every 11 hours. This data allowed its rotation period to be inferred, which helped build the first three-dimensional models of its shape. According to the simulations, 3I Atlas would have an elongated nucleus with an axis ratio close to 2.1, meaning it is approximately twice as long as it is wide. That elongated morphology could explain why its gas jets do not exit in uniform directions, but at variable angles, generating the complex structures observed in its coma and its tail. Meanwhile, space agencies have considered this object a scientific jewel. NASA, ESA, and JAXA have shared data in real time, comparing results to better understand its behavior. Studies have even been proposed for future missions capable of intercepting interstellar objects with the intention of analyzing them directly. Every observation of 3I Atlas brings humanity closer to that possibility. In short, the initial observations and chemical analyses of 3I Atlas confirm that we are facing something much more complex than a simple comet. This object acts as an open window to the past of the galaxy, offering direct evidence that the matter circulating between the stars can conserve its structure and composition for thousands of millions of years. What we are learning from it not only redefines the classification of interstellar bodies, but also expands our understanding of how the fundamental elements of life are distributed in the universe. 3I Atlas not only travels between systems, it transports in its interior the chemical history of the galaxy itself. In the study of comets, the presence of heavy metals like iron and nickel has for decades been a key clue to understanding their formation and evolution. In the case of 3I Atlas, however, the initial observations revealed something disconcerting. The spectra registered a clear abundance of nickel, but no detectable signal of iron. This finding, reported by the European Southern Observatory and later confirmed by the Keck telescope, surprised researchers because both metals are usually found together in almost identical proportions in solar system comets. That apparent absence of iron posed an intriguing question. Why would an interstellar object formed under unknown conditions show such an asymmetric metallic signature? The detection of nickel was made thanks to a set of emission lines in the visible spectrum, particularly around 340 and 350 nanometers, a region associated with the characteristic glow of metals vaporized by solar radiation. The curious thing was that these lines appeared even when the comet was still far from the Sun, in a zone where temperatures were not high enough to volatilize heavy metals. This indicated that the nickel was being released not by extreme heat, but possibly carried away by the more volatile gases like carbon dioxide. This theory was developed by a team from the Max Planck Institute for Astronomy, which proposed a particular physicochemical mechanism. When CO2 sublimes on the comet's surface, the microbubbles of gas traverse the dust layer, carrying with them tiny metallic particles. If the nickel is present in a more reactive form or in finer grains than the iron, it can be released more easily in the first phases of heating. This process had not been observed before in any other comet, making 3I Atlas the first documented case of differential release of metals in an interstellar body. For weeks, astronomers searched for signals of iron, but the results were negative. High-resolution spectra obtained by the Very Large Telescope in Chile showed the presence of multiple lines associated with nickel, but none corresponding to neutral or ionized iron. The phenomenon perplexed even the most experienced researchers. In principle, both elements have similar physical properties, similar sublimation temperatures and comparable abundances in most metallic bodies of the solar system. However, in 3I Atlas, that symmetry seemed to have been broken. The possibility that the comet had an intrinsically poor composition in iron was considered, though it was soon discarded as the main explanation. Planetary formation models indicate that heavy metallic elements like iron are common in almost all stellar environments due to their origin in Type II supernovae that disperse them uniformly in the galaxy. If 3I Atlas truly lacked iron, it would mean it formed in an extremely singular region or in an early period of the universe, before supernovae enriched the interstellar medium. However, the most probable hypothesis, supported by later data, suggests that iron was indeed present, but remained trapped in the inner layers of the nucleus, sealed under more volatile materials. When the comet began to approach the Sun and temperatures increased, the release of gases intensified and the surface eroded. It was then that observations began to show the first signals of iron. On the 12th of October 2024, the VLT spectra finally registered emission lines around 370 nanometers belonging to neutral iron. The mystery was beginning to be resolved. The pattern of gradual appearance of iron allowed the thermal structure of 3I Atlas to be inferred. Its surface seems to act as a barrier that regulates the release of different elements at different depths. First, the lighter gases and more volatile metals like nickel escape, and only afterwards do the heavier elements begin to detach. This sequential behavior reinforces the idea that the comet possesses a complex stratification, a product of compaction and cooling processes that occurred thousands of millions of years ago in its original system. The late detection of iron also allowed the proportion between both metals to be calculated. In solar system comets, the iron-to-nickel ratio is usually approximately 1:1. In 3I Atlas, in contrast, the initial measured proportion was 1.5 in favor of nickel, although this figure balanced over time as the iron began to volatilize. At the end of the most intense observation phase, the values converged towards a more similar proportion to the expected one, confirming that iron was present, but released in a later phase of heating? The finding has profound implications. First, it demonstrates that the metals of 3I Atlas behave differently from those observed in local comets, suggesting variations in their formation conditions. Second, it indicates that sublimation processes in interstellar objects can be much more complex than thought, involving physicochemical mechanisms that depend not only on temperature, but also on the texture and porosity of the material. And third, it opens a new line of research, the comparative study of metallicity in comets from different galactic origins. The data from the James Webb Space Telescope offered another revealing detail. In the mid-infrared range, emission peaks corresponding to metallic particles heated to temperatures between 600 and 800 Kelvin were detected. This means that part of the dust surrounding the comet contains metallic grains large enough to retain heat and emit thermal radiation. These particles could have formed during violent explosions within its original system, or even be fragments of material ejected by nearby supernovae before the comet consolidated. The interaction of the metals with solar radiation also offers valuable information about the comet's evolution. As 3I Atlas approaches the Sun, the vaporized metals contribute to the formation of a thin atmosphere of ionized atoms around the nucleus. This metallic corona alters the way light is scattered, affecting the observed color and the intensity of the brightness. In fact, some of the changes in the comet's greenish tone could be related not only to carbon compounds, but also to the emission of certain metals in a gaseous phase. The metallic behavior of 3I Atlas, besides its scientific relevance, offers a unique opportunity to study how heavy elements are distributed in interstellar bodies. Nickel and iron are essential in the formation of rocky planets and metallic cores. By observing how they are released and distributed in a comet coming from another stellar system, astronomers can deduce if the processes of metallic enrichment are universal or if they vary significantly between regions of the galaxy. In other words, studying 3I Atlas is also studying the origins of the material of which planets are made. The initial enigma of the absent iron transformed over time into a coherent story about the thermal evolution of the comet. What began as an anomaly ended up being one of the most solid proofs that this object is a living archive of the galactic past. Every metal released, every molecule detected is another page of the cosmic diary that 3I Atlas carries with it since its birth. Meanwhile, scientists continue monitoring its metallic glow with the hope of detecting other elements like magnesium or chromium that could reveal even more details about its original composition. But for now, nickel and iron have been enough to remind us of something essential, that even in the cold and darkness of interstellar space, the metals that were once forged in the hearts of dead stars continue traveling, waiting for the heat of a new star to shine again? Few things fascinate astronomers as much as the formation of a comet's tail. It is the visual seal of these bodies, a luminous signature that arises when the ices trapped in their interior begin to evaporate and the solar wind carries the material into space. However, in the case of 3I Atlas, nothing that was observed followed the classic pattern. Its tail behaved in such a strange way that for weeks scientists had to revise their physical models to try to explain what was occurring. In the first records taken by the Subaru telescope and the Lowell Observatory, the comet presented a tail oriented in the direction opposite to the expected one. Instead of moving away from the sun, it seemed to point towards it. The phenomenon was so surprising that some observatories doubted their own data, thinking it could be an instrumental error. But as confirmations arrived from other points on the planet, it became evident that the impossible was happening. 3I Atlas was showing an anti-tail. Anti-tails are not totally unknown, but they are extremely rare under specific conditions. When a comet has a particular orbital angle and its dust cloud disperses in a certain way, part of the material can align apparently towards the sun from Earth's perspective. However, the case of 3I Atlas was different. Simulations performed by the Institute of Space Sciences in Tokyo showed that the effect was not just geometric. The solar wind at that moment was in a state of minimal activity with a flow of particles much weaker than usual. That reduction would have allowed the heavier grains of the dust emitted by the comet to follow independent trajectories, forming a structure visible in the sense contrary to the traditional pattern. This behavior highlighted the delicate interaction between 3I Atlas and the solar environment. The stellar wind acts as an invisible current that pushes gases and dust. When that current diminishes, the denser materials cease to be effectively carried and remain in the vicinity of the nucleus. In the case of 3I Atlas, its own rotation could have projected those fragments towards the solar direction before the wind regained its strength. Thus, for several days the comet exhibited two superimposed tails, one faint and straight pointing to the sun, and another more diffuse, expanding towards the opposite side. Images captured by the VLT in Chile and the Gemini Observatory in Hawaii clearly revealed this double structure. Astronomers noted that the anti-tail was composed mainly of relatively large dust particles, microns to millimeters, while the conventional tail, which began to form weeks later, was much finer and dominated by ions. Spectral data confirmed the presence of ionized molecules of carbon monoxide and cyanogen, responsible for the bluish emissions accompanying the comet's characteristic green glow. As 3I Atlas approached perihelion, the balance changed. The solar wind intensified again, pushing the gaseous material more decisively and forcing the anti-tail to fade. In its place emerged an impressive main tail, extending millions of kilometers into space. Its form, captured in long-exposure photographs, was distinct from that of common comets. It did not present a single thin line, but a wide, slightly curved fan, like a veil of ionized gas dispersing under the combined influence of the solar wind and the heliospheric magnetic field. The color of this tail was also an object of study. Its greenish tone intensified with the passing days, and astronomers discovered that the glow came from the excitation of diatomic carbon molecules C2 and CN radicals. The fact that the tail maintained that intensity, even at great distances, indicated that the comet was releasing material in a continuous form and not through intermittent explosions as usually occurs in other cases. The uniformity of its glow reinforced the idea of a stable rotation and a porous surface that allowed a constant emission of gas. Another peculiarity was the appearance of a second, much thinner tail, composed almost exclusively of ions. Analyses performed by the Laboratory for Atmospheric and Space Research at the University of Michigan indicated that this ionized tail reacted rapidly to changes in the solar wind, curving visibly when variations in the sun's magnetic activity occurred. This offered a unique opportunity to study how heliospheric magnetic fields interact with the plasma of an interstellar object, a type of natural experiment impossible to reproduce in a laboratory. Meanwhile, terrestrial telescopes continued registering subtle changes in the comet's geometry. Every rotation seemed to modify slightly the direction of the gas jets emerging from its surface. Three-dimensional models generated from these observations suggest that 3I Atlas possesses several localized active points, possibly fractures or craters formed during its long interstellar history. From these zones, jets burst forth that, upon interacting with each other, create complex structures in the coma and in the tail, sometimes in the form of twisted filaments that move like luminous ribbons in space. Professional and amateur observers managed to capture images of these structures using specific filters. In the most detailed records, it is distinguished how the inner layers of ionized gas form a kind of faint spiral, an indication that the comet could have a slightly tilted rotation axis. The combination of this movement with the pressure of the solar wind produces patterns that seem alive, changing shape within hours? The initial anti-tail that so perplexed at the beginning later became a calibration tool for dust dynamics models. By analyzing its duration and angular dispersion, scientists could estimate the density of particles and their average size. The results showed that the dust of 3I Atlas is unusually coarse, with grains exceeding 100 microns in diameter, far above the average in other comets. This characteristic partly explains why the solar wind had so many difficulties dispersing it initially. But perhaps the most revealing detail was the stability of the tail once established. Unlike what was observed in Borisov, whose tail suffered rapid disintegrations due to nucleus fragmentation, 3I Atlas maintained a coherent structure for weeks. This confirms that its nucleus possesses superior cohesion, resistant to temperature changes and the centrifugal forces of its rotation. That resistance could be one of the reasons why the comet has shown no signs of fragmentation, despite the intense solar heat. Studies on the behavior of the tail also reveal information about the spatial environment surrounding the Sun. Every deviation, every curvature is a direct response to the solar wind and the variations in the interplanetary magnetic field. That is why astronomers take advantage of these observations to trace maps of the solar wind using 3I Atlas as a kind of natural probe. The comet thus becomes an improvised scientific instrument that allows for the measurement of conditions in the heliosphere, providing data that would otherwise require dedicated space missions. In the final weeks of direct observation before the solar brightness hit it, 3I Atlas presented a clearly defined double tail, one of dust, curved and smooth, and another ionized, sharp and bluish. That combination recalled the most iconic images of comets from the past, but with an intensity that none of them had shown. It was as if the interstellar traveler were offering one last display of its energy before submerging into the Sun's glare. When it finally disappeared behind the solar brightness, scientists had already accumulated thousands of images and spectra. Every one of those observations will be analyzed for years to understand the mechanisms that gave origin to this anomalous behavior. In the science of comets, the tail of 3I Atlas will be remembered as one of the strangest ever observed. A structure that seemed to violate the rules, but that in the end revealed the complexity of the interactions between an interstellar body and our own Sun. Every filament of that tail, every particle suspended in its green glow, is a story written in motion. They are the grains of dust that once formed part of a distant system, now carried by an alien stellar wind. From Earth, those luminous traces are the visual evidence of a journey that began long before our world existed. 3I Atlas, with its impossible anti-tail and its dance of dust and plasma, not only challenges the physical understanding of comets, it redefines the way we imagine the contact between stellar systems. For an instant, in its green glow, we see how the matter of another world dissolves in the light of our Sun, leaving behind an ephemeral trace that will tell its story for centuries. The 3rd of October 2024 marked one of the most awaited encounters of the entire tracking mission of 3I Atlas. That day, the comet passed at its minimum distance from Mars, offering science an opportunity that will not be repeated for decades. For the first time, an interstellar object approached close enough to a planet of the solar system to be observed not only from Earth, but also from another world. At a distance of just over 1.5 million kilometers, 3I Atlas crossed the plane of the Martian orbit, leaving behind a wake of gas and dust visible even for the probes orbiting the red planet. The teams of NASA and the European Space Agency coordinated an unprecedented operation to capture images from Mars. The Perseverance rover from the surface of Jezero crater and the ExoMars Trace Gas Orbiter from orbit were programmed to direct their instruments towards the sector of the sky where the comet's passage was expected. Although the apparent magnitude of 3I Atlas was very faint for the rover's cameras, the high-sensitivity sensors of ExoMars managed to register a diffuse glow compatible with the calculated position. It was the first time an interstellar object was observed from another planet. The received data showed a slight variation in brightness intensity, possibly due to the reflection of sunlight in the denser particles of its tail. The ExoMars Nomad spectrometer also detected a weak signal of emission in wavelengths corresponding to CO2, confirming once more the dominant composition already observed by terrestrial telescopes. Although the images did not show visible details of the nucleus, the simple confirmation of its passage from Mars was enough to open a new branch of planetary observation, the study of interstellar visitors from other points of the solar system. Meanwhile, on Earth, astronomers followed every movement of 3I Atlas through a combination of optical and infrared data. The comet seemed to react to the encounter with Mars in a particular way. Its brightness increased slightly during the following days, which some models attribute to a higher rate of sublimation provoked by small gravitational perturbations from the red planet. Although the force of Mars is too weak to alter its trajectory, the encounter may have induced internal vibrations in the nucleus, fracturing already stressed zones and releasing more gas. Scientists at the Jet Propulsion Laboratory took advantage of that coincidence to study the effect of small planetary forces on interstellar objects. The preliminary results indicate that although the change in its orbit was minimal, a slight modification in its rotation period was indeed detected. That difference of just a few minutes may be the imprint of the energy redistributed during the encounter with Mars. It is a reminder that in space even the most subtle forces can leave measurable marks when the instruments are sufficiently precise. For the ExoMars engineers, the event also had a logistical dimension. The probe had to reorient itself with a precision of arcseconds to avoid the interference of light reflected from the Martian surface. That adjustment allowed the spectrometer to detect a clean signal from the coma of 3I Atlas. The images processed later revealed a diffuse green cloud with an extent that, had it been seen from Earth, would have occupied more than half a degree in the sky. In Martian conditions where the atmosphere is almost non-existent, that light dispersed without distortion, offering a pure view of the interstellar gas. Scientists also took the opportunity to measure how the solar wind interacted with the comet's tail from another perspective. The position of Mars, slightly ahead of Earth, allowed the probes to register the variations of the magnetic field traversing the tail. These measurements offered an unprecedented look at how solar plasma flows around an interstellar object. The data revealed a layered structure, an inner region rich in neutral dust and an outer one dominated by highly energized ions. This configuration could be the key to understanding why 3I Atlas maintained such a stable tail despite the variations in the solar wind. In the control centers in Madrid and Pasadena, the screens showed graphs that seemed to draw a celestial choreography. The radiation peaks increased just when the comet crossed the lines of the solar magnetic field, as if space were responding to its presence. The phenomenon was not only beautiful but profoundly informative. Every fluctuation served to reconstruct the structure of the solar wind in a zone where it had never been measured with such precision before. In a certain way, 3I Atlas was mapping the heliosphere with its own tail. From the surface of Mars, the Perseverance attempted to register long-exposure images directed towards the horizon. The conditions were difficult. The planet's atmosphere scatters sunlight in a way that reduces contrast, and the rover's instruments were not designed for long-distance astronomical photography. Still, the most sensitive cameras captured a series of luminous points in slow motion corresponding to the comet's calculated position. Although the resolution did not allow for the identification of details, those images have historical value. It is the first time we see from another world an object that comes from outside our solar system. The event was followed by thousands of enthusiasts on Earth. Astronomical centers opened live streams, and scientific forums filled with discussion about the implications of these observations. Some researchers proposed that the ExoMars data could be used to refine the laws of interaction between plasma and dust in low-density environments, a crucial topic for the physics of comets and exoplanets. In the days following the encounter, computational models recreated the exact trajectory of 3I Atlas in relation to Mars. The simulations showed that the planet's gravity slightly altered the shape of its tail, generating a slight curvature associated with the interaction with the Martian magnetic field. That perturbation was small but detectable, and provided valuable data about how planetary magnetic fields influence ionized matter traveling through space. During the weeks the comet remained visible from Mars, the solar wind experienced a series of moderate storms. The ExoMars instruments detected how those waves of particles affected the intensity of the ionized tail. For the first time, the reaction of an interstellar object to a solar storm was measured directly from another point in the solar system. The observed fluctuations confirmed that 3I Atlas possesses an unusually high electrical conductivity in its coma, possibly due to the high proportion of carbon and oxygen ions. Although the images from Mars do not show spectacular details to the naked eye, their scientific value is incalculable. They offer a second perspective, free from terrestrial atmospheric interference, that allows for the three-dimensional reconstruction of the comet's structure and its tail. The fact that an object formed in another stellar system was observed by instruments manufactured by a civilization from Earth and operating from another planet is in itself a symbol of how far human curiosity has reached. While 3I Atlas continued its trajectory towards the Sun, scientists knew it would soon disappear behind the solar glare, hidden for weeks before reappearing in the morning sky. But the observations from Mars remained recorded as a historical mark. the first interplanetary collaboration to observe an interstellar traveler. The comet had traveled for thousands of millions of years through the galactic darkness, only to witness for an instant the curious gaze of a species that has just become a planetary civilization. As 3I Atlas continues slowly moving away from the Sun, its light begins to fade amidst the glow of the terrestrial dawn. For now, the comet remains hidden behind the solar brightness, invisible even to the most sensitive telescopes. This phase of silence is just a respite before the next opportunity, its reappearance in early December, when it will be visible again in the dark sky of the early morning. For scientists, that moment will be crucial. It will be the first occasion in which they can compare its state before and after the perihelion, and with that measure how much its structure has changed after facing the extreme heat of a star that is not its own. The Sun's relentless radiation has acted as a natural laboratory. Every particle detached, every variation in the brightness of 3I Atlas constitutes an ongoing experiment on the effects of stellar energy on interstellar matter. The observatories that could not follow it during the weeks of greatest solar luminosity await its return to the visible field anxiously. Coordinated campaigns have been prepared among telescopes of different wavelengths, from optical to radio, to track the chemical and structural changes the comet may have undergone. It is expected that part of the expelled material will form a thin stream of dust that will accompany its trajectory for months, allowing the composition of the layers that the Sun managed to vaporize to be reconstructed. On the 19th of December, the comet will reach its maximum approach to Earth at a distance of 1 astronomical unit. It will represent no risk, but its passage will offer a unique opportunity to perform simultaneous observations from both hemispheres. The observatories of La Silla, Mauna Kea, Cerro Tololo, and the Gran Telescopio Canarias have already reserved tracking time. Astronomers plan to measure the density of residual gas in its coma and the distribution of dust in the tail, comparing this data with that obtained before the perihelion. This way they will be able to evaluate how much material 3I Atlas lost and how solar radiation altered its proportions of carbon, oxygen, and metals. Attention will also focus on tracking the nucleus. If the comet's surface suffered fractures, the light reflections should show periodic variations in its brightness curve. This type of oscillation could reveal a change in its rotation period, perhaps provoked by asymmetric gas jets that acted as natural thrusters during its close passage by the Sun. If confirmed, it would be a direct demonstration of how sublimation can modify the rotational movement of an interstellar body, something that had only been inferred in solar system comets. After December, 3I Atlas will begin its slow retreat. Its trajectory will lead it to traverse the outer region of the system, where it will meet Jupiter for the last time in March 2026. Although the distance will be several million kilometers, the magnitude of the giant planet and the power of its gravitational field could subtly alter the comet's speed and direction. Astronomers trust that the Juno probe, still operative in Jupiter's orbit, will manage to capture some signal or image of this distant encounter. Even a minimal detection would serve to refine the models of gravitational scattering that govern the behavior of interstellar visitors when passing through planetary systems. By then, 3I Atlas will have completed its brief stay among us. Its path will continue moving away from the ecliptic plane until it is lost again in the galactic darkness. Its hyperbolic velocity guarantees it will never return. This one-way journey is what makes it an invaluable witness. Everything that can be measured in the coming months will be literally the last word that science obtains from this traveler. Once it crosses the boundaries of the solar domain, no current technology will be able to observe it again. However, the information collected until now has already transformed contemporary astronomy. The chemical data reveal that interstellar comets are more diverse than imagined. They are not simple wandering fragments, but archives of distinct physical conditions, relics of stellar environments that perhaps have already disappeared. Every one of the molecules detected in 3I Atlas, from the CO2 that dominates its coma to the traces of nickel and iron released with the heat, expands our map of galactic matter. Furthermore, the study of its thermal behavior has demonstrated that interstellar objects can conserve their integrity much longer than expected. The fact that 3I Atlas did not fragment during the perihelion indicates that its internal structure possesses an unusual cohesion, probably the product of a compaction process that occurred in a high-pressure environment or of repeated freezing cycles throughout its history. This type of data helps refine models about how cometary nuclei form in other regions of the galaxy and how they could survive the violent gravitational ejections that expel them from their home systems. The possibility that its nucleus is composed of alternating layers of CO2 ice and metallic dust has led some scientists to suggest that 3I Atlas could represent an intermediate class between comets and icy asteroids. That category, merely theoretical until now, would describe objects that combine the structural hardness of asteroids with the chemical volatility of comets. If confirmed, it would mean that 3I Atlas is the first known example of a new type of hybrid interstellar body. Beyond the technical data, the passage of 3I Atlas has a profound symbolic value. It reminds us that the solar system is not a closed space, but a temporary station in a continuous flow of galactic matter. Fragments from other suns cross our neighborhood from time to time, bringing with them stories written in ice and metal. To observe them is, in a way, to listen to the echoes of cosmic evolution. Space agencies are already planning the future. NASA has announced that the next generation of observatories like the Nancy Grace Roman Telescope and the Vera Rubin Observatory will be capable of detecting interstellar objects with months of anticipation, allowing even the rapid launch of automated probes to intercept them. The experience acquired with 3I Atlas will be the foundation of those projects. Every parameter measured, every light curve will serve as a reference for missions that in the future could directly analyze the surface of an interstellar visitor. When the scientific community publishes the final results, 3I Atlas is expected to be consolidated as one of the most studied objects in the modern history of astronomy. Its data are already being compared with those obtained from Oumuamua and Borisov to create a catalog of common properties and essential differences. This catalog will allow for the estimation of how many of these travelers could exist in the galaxy, and with what frequency they cross the domain of the Sun. Some preliminary calculations suggest that on average an interstellar object the size of 3I Atlas could enter our system every 80 to 100 years, although most go unnoticed. Knowing this invites us to look at the sky with a new awareness. At any moment, another visitor could be approaching. When the telescopes capture it again in December, astronomers will observe not just a comet but a survivor. Its passage by the Sun will have modified its surface. Perhaps some fragments have detached, perhaps its rotation is different, but it will still be there, visible for the last time before its definitive departure. Its brightness, although faint, will represent the closure of an observation cycle that united scientists from all continents and instruments on Mars, Earth, and in space. In that farewell is summarized the very essence of scientific exploration: to look at the unknown, to understand the fleeting, to record the unrepeatable. 3I Atlas came from afar, traversed our system with the indifference of a traveler seeking no destination. And yet, in its brief encounter, it left us with knowledge, questions, and a new perspective on our place in the universe. When it finally disappears behind the glow of the stars, we will know that part of its journey will continue with us. In the data, in the models, and in the images that revealed its passage. It will have returned to the silence of interstellar space, but the echo of its visit will persist in the laboratories, in the observatories, and in the minds of all who looked up to see it cross. 3I Atlas belongs to no sun, but for a few months it was part of our history. And perhaps somewhere in the cosmos, another world looks towards its sky and sees a similar traveler passing by, wondering like us, what secrets are guarded by the matter that comes from the stars.